dun 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 dun. It's time for section 8.3. Okay, that was really nerdy. Estimating a population mean. So we're going to do what we did with proportions in 8.2, but now we're going to work with means. The one sample z interval for a population mean. We can calculate a 95% confidence interval by taking, or any confidence interval, the estimate. Uh-oh, here we go again. Why is that not working? Grr. Okay, let's try this again. Alright, so we can take the estimate plus or minus that critical value, and remember you can go find that if it's a 95% above the 95%, so whatever confidence interval you're at, and then times the standard deviation of the statistic. Just kind of seeing it all with the normal density curve. And here with means, the standard error now is your sigma divided by your square root of n. This needs to be aligned really quick. Sorry about that. Hopefully you're having a good day today. I definitely am. Gonna have some Jimmy John's for lunch. Okay. So in a one sample z interval, basically you're going to take your sample statistic here, x bar plus or minus your z star times your standard deviation. The margin of error is just that z star times your standard deviation. And when you want to try to find a margin of error to be within a certain amount, sometimes you can find like how many you're going to need in your sample. So what value of n are you going to need to take if you need your margin of error to be within a certain amount? So you could always say, like, let's say we wanted our margin of error to be within 0.01. So I could set this up and solve for the n going on. Alright, so researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey that is often used in a laboratory experiments. They would like their estimates to be within 1 milligram per deciliter of the true value of mu at 95% confidence level. A previous study involving this variety of monkeys suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. So let's see what our sample might have to be. Get my calculator out too. We can go find our critical value on our formula sheet. Remember, it's right above. And basically, we're going to take our critical value then times that standard deviation, which was 5. That was your sigma, divided by what n, and it wants to be within 1 milligram. So we want that standard error to be less than or equal to 1. Okay, so we can multiply both sides by the square root of n. So I have 1.96 times 5 is 9.8, is less than or equal than the square root of n. Dividing by 1 doesn't really change anything, right? Sorry. So then I can square both sides, so 9.8 squared. So I have 96.04. And you can't have a fraction of a person, and if you go down to 96, you're not going to be within 1. You're still going to be too big. So you're always going to round up here. So your n, your n has to be 96 or more to be within, or sorry, 97 or more to be within 1 milligram. Okay, at the 95% confidence level. And if you did your math a little bit differently but still got the same answer, that's fine. You may have done some operations a little bit different. Okay, to assess the accuracy of a laboratory scale, a standard weight known to weigh 10 grams is weighed repeatedly. The scale readings are normally distributed with an unknown mean. This mean is 10 grams if the scale has no bias. In previous studies, the standard deviation has been about 0.002 grams. How many measurements must be averaged to get a margin of error of 0.0001 with 98% confidence? Show your work. So see if you can do this one, and then once you've worked it out, unpause and see if you get the right answer. Okay, so I have my setup, and that's going to lead me to get 22. So if you want a little bit more help, so 2.33 times 0.0002 is 0.2366 equals 0.0001 square root of n. So I just took this guy times that guy and brought that over. Then I'm going to divide the 0.00046 by 0.0001. So I get 4.66. Well, I want it to be less than or equal to, right? Less than or equal to now the square root of m. Square both sides. So 21.7156. So n has to be bigger than 22. 22 is the minimum. Okay, so when your sigma is unknown, you're going to use something called the t-distribution. So you cannot use z distributions when your sigma is unknown. If you want to read through that a little bit, you can. So in your chart, you have the t distributions, and there's something going along with it called degrees of freedom, which we're going to get to. So this t distribution has a different shape than the standard normal curve. Okay, it's still going to be symmetric. However, it has much more area in the tails. So it's got more variance going on. It's more spread out. So your t, you can see here, it's going to be more spread out, whereas your z is going to have less variance. There's a higher concentration in the middle here. Okay, so t has more area in the tails. T-tails. Okay, and again, the t is going to tell us how far away from that x bar we go out. Okay, just like we did the sigmas that we went out from the mu, the t is still going to tell us how many standard deviations away we are from the x bar. But we have to work with degrees of freedom. So degrees of freedom, when we perform inference about a population mean mu using a t-distribution, the appropriate degrees of freedom are found by subtracting 1 from the sample size. So all you have to do is take your sample size minus 1 to get your degrees of freedom. So, draw an SRS of size n from a large population that has a normal distribution with mean mu and standard deviation sigma. And the statistic here, t, you can see what that formula equals, has the t distribution with degrees of freedom n minus 1. And that statistic will have approximately t sub n minus 1 distribution as long as the sampling distribution is close to normal. Okay, so you may ask for a better explanation of what degrees of freedom are all about, and there's really no simple answer. From now, just simply know that the shape and the spread of the t-distribution depends on the degrees of freedom. So as I increase in size, my degrees of freedom are going to increase. So like let's say I had 2 degrees of freedom, and then I had 4 degrees of freedom, and then maybe I had like 20 degrees of freedom. So it's going to become more and more normal with the degrees of freedom. As they increase, you're going to have less area in the tails. All right, William Gossett. He actually invented this, he discovered, I should say, the t-distribution, and this is very interesting. So the t-distribution and the t-inference procedures were invented by William Gossett. He worked for the Guinness Brewery, and his goal in life was to make a better beer. He used his new t procedures to find the best varieties of barley and hops. Gossett's statistical work helped him become a head brewer. When Gossett was testing beer, he noticed that when he standardized the value of X bar for his samples using the sample standard deviation, he got values way beyond plus or minus 3 standard deviations going on. So this happened a lot more than expected. So this led him to explore the distribution and how it was different than that distribution of Z, and it helped him discover the T distribution. Crazy, right? Math is everywhere. Okay, so this is a little bit what we talked about. Here you can see as T increases, there's less area in the tails. It's more concentrated, less variant. And that's kind of what we talked about as well. Okay. And we can use our table and our formula sheet to help find the T stars. All right, so suppose you want to construct a 95% confidence interval for the mean mu of a normal population based on an SRS of size n equals 12, and what critical T star should you use? So if I go look at that formula sheet, and you should have it out right now, pause if you are looking for it. Okay, so if I go to that formula sheet, I can see that I have a sample size of 12, so I'm going to have 11 degrees of freedom, and I'm going to go up from a 95%. So I'm going to take out 11 degrees of freedom and go up from the 95%, and I can see where they overlap. It's 2.201. So that's going to be your critical value here, your T star. Now, you can also find your critical value going on in your calculator. So to think about that, so if I have a 95% confidence interval going on, then how much is left in the tails? Well, that would be 5%. So when I'm doing an inverse T, if I want to find that value, then I've actually have covered, so that would be 2.5%, and that would be 2.5%. So all the way from here up, I've got 97.5% covered. So if I want to find that T value, then when I do my inverse T, and you can go second vars, and inverse T is number 4. Okay, so that was number 4 right here. After second vars, I'm going to not put 95%, but I'm going to put the 0.975%, or not percent, but 0.975, and then comma the degrees of freedom. So this is all the area up to that value. Okay? And here you can get an even more accurate critical value than what the table provides. So find the critical value T star that you would use for a confidence interval for a population mean mu in each of the following situations. If possible, check your answer with technology. And I'm going to let you see if you can go find these, and you can put them in your calculator, or you can find them in the chart. And here is what they would be to 3 decimal accuracy. So what critical value T star from the table would you use for a 90% confidence interval for the population? What if you had this value of size 77? So in your chart, you don't really have that. You're going to have to like go up to the nearest one, or down to the nearest one, I guess would be safer here. Okay, so you're going to have to go down. So in this case, you definitely want to use your technology. So I'm going to do an inverse T of point. So if I have my 90%, So that means I have 5 and 5, so this would be 5% here, 5% here. So all of that would be 0.95, comma, degrees of freedom would be 76. So inverse T, second vars, number 4, 0.95, comma, 76, I got out 1.665. So if you did it in your chart, when you round it down here, you're going to see that you're going to get out 1.671. Well, that's not nearly as accurate as what you should have. Okay? So your calculator can definitely help you out here. So constructing a confidence interval for mu, when the conditions for inference are satisfied, the sampling distribution for x bar has a roughly normal distribution. Because we don't know sigma, we estimate it by the sample standard deviation s sub x. So you can't hardly see that, but that says s sub x over the square root of n. Okay? When you know you have a mean of x bar. So here you're going to have to use that sample standard deviation since you don't know the sigma. And that's why you're using t's. You use t's if you don't know the sample or the population standard deviation. So you can create your confidence interval by doing your x bar plus or minus your t star, and since you don't know the population standard deviation, you're going to have to use your standard deviation right there in the formula to create your confidence interval. Okay. So a study of commuting times reports the travel times to work of a random sample of 20 employed adults in New York State. The mean is in minutes and the standard deviation for the sample is 21.88 minutes. What is the standard error of the mean, and interpret this value in context? Okay, so, oops, let's go ahead and write that out. So our standard error, we're going to have 21.88 divided by the square root of 20. Okay, so here I can see that that's going to be my standard error. In repeated sampling, the average distance between the sample means and the population mean will be about 4.8925 minutes. I think you have one on your test like that. Okay, so you still have to check your conditions. You must check conditions unless the problem says conditions are already met. Always check your conditions or you're going to lose a lot of points. Random, the data comes from a random sample of size n, and that's usually stated in the problem. Normal, it needs to be greater than or equal to 30 for means. Remember, proportions is that n times p and n times 1 minus p has to be greater than or equal to 10. But for means, n has to be greater than or equal to 30. Or you can make a box and whiskers and see if there's any outliers or any strong skew, okay, if it's not greater than or equal to 30. Independent, the method for calculating a confidence interval, assumes that individual observations are independent. To keep the calculations reasonably accurate when we sample without replacement from a finite population, we should check the 10% condition, verify that the sample size is no more than 1/10 of the population, and we've been doing that. All right. So here we go. Okay. We can only use it when it's normal, population. We got this down. We need to make an interval. So on your AP exam formula sheet, you know this formula on there. So you're going to have to know, if you do not know the population standard deviation, you can use it, the sample standard deviation, to approximate it, okay? And that is not going to be in there for the standard error formula. It's only going to be when you see the sigma on the formula sheet. But you're going to need to know that. So it's okay when you don't know sigma to use S sub x, okay? All right, video screen tension. A manufacturer of high-resolution video terminals must control the tension on the mesh of fine wires that lies between the surface of the viewing screen. Too much tension will tear the mesh, and too little will allow wrinkles. The tension is measured by an electrical device with output readings in millivolts. Some variation is inherent in the production process. Here are the tension readings from a random sample of 20 screens from a single day's production. So the first thing I do as soon as I see all of those is I would go make a list. So stat, edit, list 1, go put them all in there. 269.5. So I'm doing that right now. Hopefully you are too. Oops. Stat, edit. I got 304. Do. I'm on my second line. Am I beating you? Are you beating me? Are you faster at this? 43.3. Okay, 74.6. Whew! Alright, got all 20 in mine. So now let's see, it says construct and interpret a 90% confidence interval for the mean tension mu of all the screens produced on this day. Okay, so we got to determine, we're constructing a 95% confidence interval. Are we dealing, the first choice I need to make, are we dealing with categorical or quantitative data? So we have quantitative data, so we're going to be working with means. Now within means, I need to know, am I going to be working with T's or Z's? So T's are when sigma is unknown. Z's are when sigma is known. So do you know the population standard deviation anywhere in this example? No, you do not. So we are going to be working with a one sample T interval for means. So one sample T interval for means. Okay? And we're going to be doing this at a 90% confidence level. So let's check and make sure that our conditions are met. We cannot do this unless our conditions are met. Got it? Okay, say that to yourself again. We cannot do this unless our conditions are met. All right, so we are told that the data comes from a simple random sample. So, yep, it's random. Normal, since the sample size is small, what row? We must check whether it's reasonable to believe that the population distribution is normal. So, we've already got our list made. Let's go to second plot, stat plot. So second y equals, and I'm going to go turn on my first box and whiskers that shows any outliers, if there are any present. And I want to zoom stat. Make sure you don't have anything else in your y equals. Zoom stat, which is zoom 9. And I got my data. Oops. To look like this. That's the one I like to make. You can make a dot plot, you can make a normal probability plot, but I like using the box and whiskers plot. I think it's really easy to do when you already have everything in your list. So that doesn't look really skewed at all. That looks almost perfectly symmetric and there are no outliers going on, or I would have had dots from that first box plot. So we're good to go. And then independent, we were sampling without any replacement here, so we have to check our 10% condition. So we have to assume that 10 times our sample of 20, that our population has at least 200 video terminals were produced this day. All right, so in our calculator now, we can go stat, calc, one variable statistics. And we can see that our mean is 306.32, and our standard deviation, we have to use the S, not the sigma, because this is a sample. So we want 36.21 or 36.2092839 if you even want to be more exact. Okay, so make sure you're getting from the sample. And if you didn't get those, you put them in your list 1 wrong. Now, this is going to be one way, and then I'm going to show you an easier way, okay? So here we had a sample of 20, so we're going to have 19 degrees of freedom. Oops, that got a little off. 19 degrees of freedom. With, we're going to go up from a 95% confidence interval. And we can see that our T-star here, where they overlap, is going to be 1.729. So now when I construct, I can do my sample mean, my statistic, plus or minus my critical value, divided by my sample standard deviation here, because we don't know sigma, or times our sample standard deviation, divided by the square root of n. Simplifying it down, we get an interval like this. So we are 90% confident that the interval from 292.32 to 320.32 millivolts captures the true mean tension of the entire batch of video terminals produced that day. Okay, so now I'm going to show you a different way that you could do it. We'll come back to these, okay? Maybe. I didn't think it was that far away. Okay, so let me go back. I'll just talk about it. I thought I had it in here. Almost. Okay, so the other way you could do, and we've been using our calculator, is we can go to stat. No, just kidding. Oh my gosh. Yeah, I was right. Okay, sorry. Long day. Okay, so stat. And then go to your tests. And in this case, we are doing a T, one sample T interval. So we need to scroll down, and I see on number 8, I get a T interval. So we want to pick number 8. Then we have 2 options for the input. Do we have data or do we have statistics? Well, we had all that data that we already put into list 1, so we're going to select data. And then hopefully list 1 is already listed on the list. That's where we put it. Frequency is just always 1. Your confidence interval here was 0.95. And then we can hit calculate. And what do we get out? Something even more exact, okay, from not having to round so much. That is nice. So we can be even more exact with our calculators. And that's the way I like to do it. But it's always nice to see the setup of where it all comes from. All right, a one sample T interval for mu, environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhausts from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides. Researchers collect data on the NOx levels in grams per mile for a random sample of 40 light-duty engines of the same size. So it tells us the mean reading was this guy, and the standard deviation was that guy, and that was for a sample of 40. So here, that's going to equal x bar, because it's a sample, and this will equal s sub x, because it's a sample. So construct and interpret a 95% confidence interval for the mean amount of NOx emitted by light-duty engines of this type. So I'm going to go where I went again. I'm going to go stat, over to tests, and since I do not know my population standard deviation, I use a t-test. So I'm going to be using a one sample t-test. So I can check my conditions. So here we're going to be using a one sample t, oh sorry, did I say test? Sorry, interval. It asked us to do an interval. One sample t interval for means. It was random, it said so. Normal, well, n is 40, so that is greater than or equal to 30, so we're good to go there. And independent, this is without replacement, so let's do 10 times our sample, and we need to assume that there are at least 400 light-duty engines of this type. That seems appropriate. So now we can either do our formula, or we can put in our calculator, stat, s, 8, go to your t interval. And in this case, I do not have data, I only have the statistics. So what were my statistics I'm going to put in? So my x bar we found to be 1.2675, and my sigma was 0.3332. My n was 40. My confidence level is 95%. I can hit calculate. Okay, so here, if we did it out in the calculator, I got 1.1609 to 1.3741, which is more accurate than the rounding that we did by using that interval. Okay, so our conclusion is that we are 95% confident that the interval from, you could either say the one from by hand or the one from the calculator, contains the true mean level of nitrogen oxides emitted by this type of light-duty engine. So, B says the Environmental Protection Agency sets a limit of 1 gram a mile for NOx emissions. Are you convinced that this type of engine has a mean NOx level of 1.0 or less? Use your interval from A to support your answer. So let's look at this. Oops. What did it say? We got an interval of 1.16 to 1.37, and so let's see, 0.1 is definitely lower than that interval, so I don't think they're being very accurate here, okay, of saying that it's 1.0 or less, because we're saying that the mean is definitely greater than that. So I think that they are lying. Okay, you guys try this one. See how you do. You could read that if you wanted to. Let's do this one from this mini tab. Okay? So here in an earlier example, we constructed a confidence interval for the mean level of NOx emitted by a specific type of light-duty car engine. The original random sample actually included 41 engines, but one of them recorded an unusually high amount, 2.94 grams per mile of NOx. Upon further inspection, this engine had a mechanical defect, so the researchers decided to remove it from the data set. And now this is a Minitab computer output to give some numerical summaries for the NOx emissions in the original sample with that outlier removed. So let's construct our confidence interval now. So we can take our mean plus or minus our T star. So let's see, if our N is 41 and it wants it with a 95%, I think it was, 95% confidence interval, you can look in your table and find that, or you could actually do second vars, inverse T, 0.975, comma, 40, was it with 95%? Go back. Did it say? I'm not getting that. What if it was 90%? Okay. I don't remember what percent it was to put in here. Grr. Oh, I think it was 95%. 975. Okay, yeah, so at 95% on the table, that's what they got. And if you put it in your calculator, I got 2.02107.537-ish. So that's pretty good. I think that the table in this case is fine. And then we can do plus or minus the standard deviation divided by the square root of n, and simplifying it down to get to this interval. So I still think they're lying because 1 is below, okay? All right, except in the case of small samples, the condition that the data comes from a random sample or randomized experiment is more important than the condition that the population distribution is normal. Okay, so here are some practical guidelines. You can read through those. An AP exam common error. When students are constructing a one sample t-interval for a population mean based on a small sample, many students neglect to graph the sample data and comment on the normal condition. So for instance, if your n is greater than or equal to 30, you just need to state that your central limit theorem applies. But if your n is less than or equal to 30, you need to show this. Okay, now I know you can't show it for me, so you just have to describe what you're doing because there's no way for me to see it. But definitely put it on the AP test, okay? So simply saying that we assume normality will not earn full credit when the data is provided. You have to show a graph or give appropriate comments that address the normality of the population. So determine whether we can safely use a one sample t-interval to estimate the population mean in each of these settings. All right, oops, let me go back. So in A, let's see, is a histogram of the percent of each state's residents who are at least 65 years of age. So looking at that, you definitely have 50 states. Where am I going? So what does it say? We have data on the entire population of the 50 states. So formal inference makes no sense. You already know what's going on states. You have that. Okay, that you have census and different things. So okay, let's look at B and C. That's what I really want to talk about here. So B, if you're looking at that, you have a sample size less than 30. And same thing on C, you have a sample size less than 30. Now C is skewed to the right and B is skewed to the left, but C skew is a lot less than B's, and B, it looks like you might have some outliers where I don't see that going on in C. So B, I think that since it's strongly skewed and you have some possible outliers, no, you're not going to be good. And in C, since it's just a mild skew and there's no outliers, then you'd be okay. Oh, there it is. That's what I was looking for earlier. So here's if you do the interval in your calculators. We've already talked about that. If you'd like to try this one, go ahead. Again, don't forget to check all your conditions. Okay, so in the sections we learned about intervals for the mean, and when you're dealing with means, is sigma known or is sigma unknown? If sigma is known, you're going to use t's. If sigma is unknown, you're going, sorry, I think I just said that wrong. If sigma is known, you're going to use z's. If sigma is unknown, you're going to use t's. Okay, so not only are you breaking it down between means and proportions, but now within means you have to break it down again. Check your conditions, check your conditions. Confidence intervals, and we're done with module 8. Woohoo! When you have sound this time. Okay. Good luck on your test.